Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the JFET. Let's start. By the time you finish this lesson, you will learn JFET structure, JFET operation, pinch-off voltage, and JFET I-V characteristics. In the previous lectures, I introduced the most important electronic switches that we use in switching power conversion applications. So far, I covered thyristors, GTOs, triode, BJT, MOSFET, and IGBT. In this lecture, my aim is to introduce the junction field effect transistor, or JFET. JFETs are normally not used as switches in power electronics converters, mostly because they are normally in the on state. However, they are sometimes used in very low voltage and low current power conversion applications. JFETs are today used to build unstable resonators in environmental energy harvesters. Since there is a niche application for JFETs in power electronics, I was thinking that this is a good idea to wrap up this course with a lecture covering JFETs. In general, JFETs are divided into N-channel and P-channel. Here is the N-channel JFET, and this is the P-channel JFET. As you can see, the JFET has a symmetrical design and 3 terminals. The left terminal is called the drain, the right terminal is called the source, and the two P+ regions are electrically connected to each other, and they form the gate terminal. This is the symbol we use for the N-channel JFET in circuit schematics, and this is that of the P-channel JFET. In terms of the operation principles, the N-channel and P-channel JFETs are the same in a symmetrical manner. As a result, to discuss the details of the JFET operation, I use the N-channel JFET. Whatever is discussed about the N-channel JFET is conceptually applied to the P-channel JFET. So here I have the N-channel JFET. The two P+ regions are connected to each other, making the gate terminal. The two P+ regions are in contact with the N-type semiconductor. As a result, we have two depletion regions. I am assuming that before you watch this lecture, you have watched all the previous lectures in this course. This is why I do not spend time to discuss why the depletion regions are made. Anyway, in the depletion regions, we do not have any charge carriers. Let's connect a voltage source called VDS between the drain and source, and one connected between the gate and source. As long as VGS and VDS are 0, the depletion regions remain as are. Since the current flow in the N region is not obstructed, the N-channel JFET is normally closed or is in the on state when unbiased, and the N region behaves as a resistor. Let's now increase VDS while keeping VGS 0. What happens now is that the P+ semiconductors have 0 potential, and the left side of the N semiconductor is connected to a positive voltage, while its right side is connected to the ground. As a result, there is an electric field directed from the left to right in the N semiconductor. The voltage amplitude across the device length is plotted here. On the very left, the voltage equals VDS, and on the very right, the voltage is 0. As a result of this electric field, there is a current flow of electrons from the right to left. At the same time, there is another phenomena is taking place since P+ semiconductors have 0 electrical potential and the drain has positive potential. The PN junctions on the top and bottom of the device are reversely biased. If you remember the lecture on the PN junction reverse bias, you already know that under the reverse bias, the depletion region expands by increased reverse voltage. In this situation, as I mentioned, since the top and bottom PN junctions are reversely biased due to the applied VDS, by increasing VDS, the depth of the depletion regions increase. The closer the depletion region to the drain is, the more depth of the depletion region is achieved. On the source side, since the voltage level is 0, the depth of the depletion region does not change noticeably. If I keep increasing VDS, the depth of the depletion regions gets larger and larger, and finally in a region close to the drain, the two depletion regions touch each other. The VDS voltage at which the top and bottom depletion regions touch is called the pinch-off voltage, which is shown by Vp. For any VDS below the pinch-off voltage, increased drain to source voltage causes the drain current to increase. Above the pinch-off voltage, you may expect the current flow to stop because the channel is closed. However, it does not. The drain current remains constant despite the fact that the channel is closed. Above the pinch-off voltage, there is an electric field on the left and right side of the pinch-off region. When electrons get close to this electric field, they are captured by the field, accelerated, and then jump to the other side through the pinch-off region. So far, I kept VGS 0. What if I apply a negative voltage between the gate and source? By applying a negative voltage to the gate source while VDS is 0, we are making the top and bottom PN junctions under the reverse bias, and therefore the depth of the depletion region increases. So when we apply VDS to the device, the pinch-off happens at a lower VDS and the current gets saturated. In other words, the pinch-off voltage of the JFET changes by changing the gate to source voltage. Let's take a look at the IV characteristic of the JFET. For a gate source voltage of 0 below the pinch-off voltage, the current increases almost linearly by increased VDS. Above the pinch-off voltage, the current gets saturated. By applying negative gate source voltages, the pinch-off voltage gets smaller, and at the same time, the saturation current gets smaller too. If I connect the pinch-off voltages of each curve in this diagram, I can define two regions. On the left side of this curved line, the JFET is in the ohmic or linear region, and on the right side, the JFET is in the saturation region. If the negative gate source voltage is large enough, the JFET is in the cutoff region where no drain current can pass through the device. In this lecture, I discussed the JFET structure, JFET operation, pinch-off voltage, and JFET I-V characteristics. This lecture wraps up the basics of the semiconductor course of Peacademia. Thanks for taking this journey with me.